Hello AP Chemistry and welcome to solution formation, right? So here we're going to talk about different aspects of forming a solution, right? Where a solution means that my solute has to be able to interact with my solvent via a shared IMF, okay? The solute has to be able to interact with the solvent via a shared IMF. When we look at the energetics of that, right, what that means, right, in your book talks about how we have to separate my solvent particles. And if we think about separating things, right, like we talked about in the previous chapter, anytime we separate things, that costs energy, okay? We have to separate my solute particles. Again, costs energy, okay? And that's what this part is, right? That's energy that has to go into the process, right, to separate my solute and separate my solvent particles. When we mix them together, we introduce or reintroduce a force of attraction, right? Just like all, right, coming together of particles, right? If there is a favorable IMF, then then letting those particles get close enough to interact is always going to be releasing energy, right? And it's the balance between those two forces that determines whether or not the dissolving of a substance is endo or exothermic, okay? If it's exothermic, by the way, what are we going to observe as the dissolving happens? Right, we're going to have an increase in temperature of my water that we're dissolving in, okay? Because more heat is being released when the solute and solvent interact via a shared IMF than went into separating my particles, okay? Over here we have the opposite situation wherein we have to separate my solvent, separate my solute, and then turns out that we do get energy back, just not enough to make up for how much went in. And in this case, my dissolving would be endothermic. And again, we would notice a, decrease in the temperature of my water. Yes? Fantastic. Now this diagram is what we would use to discuss why increasing the temperature increases the solubility of my solid solutes, right? Because if we increase the temperature, right, then we actually provide energy input for these two endothermic processes, right? Which means that these happen more readily, blah, blah, blah. Okay. Now, pressure and gaseous solutes. Note that when we talk about pressure effects, we have to be talking about a gaseous solute, okay? Which means that if we were talking about a solid solute, like if we were talking about NaCl, for example, in water, and we wanted to discuss pressure, no, right? That's a trick question, right? In that it has no effect because NaCl is not a gas, right? Which means it's not subject to changes in pressure. Here, though, if we have a gaseous solute that's above the water, right, the gas particles come and go as they will, right, and some stay dissolved, right? If we increase the pressure of my gas particles, right, meaning that there are more collisions with the surface of the water, right? If we increase the pressure, it means that my solute particles will have more collisions with the surface of the water, right? Because that's what pressure is, right? Collisions with surfaces in the vicinity, right? Likewise, so we'll increase the collisions with the surface of the water, which means on average, more of my gaseous solute will remain dissolved, okay? Now, temperature, we just said that as we increase the T, right, we increase solubility. All right? Now, for gases, what's the case? Right, if we decrease the temperature, we increase the solubility. Right? And if we think about that, right, thinking about what we know about gas behavior, like we talked about last year, if we decrease the temperature, they have less kinetic energy and they're less likely to be able to leave the liquid phase, right? They are less likely to leave the solution, right? And your book points out several neat observations that we would pay attention to, right? For example, when you get the glass of tap water and you let it sit for a while, right, then we see those gas bubbles form, right, as the gas starts to leave my liquid, okay? Which is why, coincidentally, right, if you have a soda, for example, if you have a can of soda that's at room temperature, right, the immediate flavor when you take a sip is different, right, than a freshly opened soda straight from the refrigerator, right? And if you've never tried that, right, put a can at room temp, put a can in the fridge, give them a few hours or overnight till it's decidedly chilled, and then pop them open in the morning, right, or maybe the next afternoon because that's weird. And then you'll see, right, there's a difference because if we get more of that CO2 to dissolve, right, then if more of that CO2 dissolves, more of that CO2 has the opportunity to form carbonic acid, which means it gives it a more acidic pop than it does at room temperature, okay? So anyway, thank you for listening. to talk about a little bit about IMFs and solution formation. I hope that all of this makes sense to you because we're going to discuss it at length tomorrow in our demonstration. Thank you for listening. Be good, and I'll see you soon. Bye.